Welcome to this Australian BioCommons and Pawsey Supercomputer webinar series. Through sessions like these, we hope to share useful information about the latest digital techniques, data and tools. In hearing from local and international peers, the Australian BioCommons aims to support Australian bioscientists to deliver their best environmental, agricultural and medical research. Collaborating with Australian BioCommons to bring you this webinar is the Pawsey Supercomputing Centre, one of Australia's two Tier 1 supercomputing centres. Pawsey is an unincorporated joint venture between CSIRO and 4 Western Australian universities. My name is Christina Hall and I'm the Australian BioCommons Training and Communications Manager. And co-organising this webinar series is Anne Backhouse, Pawsey's Education and Training Manager, who you'll be meeting during question times today. Before we start, we'd like to acknowledge the traditional owners of the lands on which we work. We pay our respects to the elders past, present and emerging, for me in Melbourne of the Wurundjeri people and in Perth, the Whadjuk people. We hope you find today's session engaging and we look forward to hearing your questions throughout. Our speaker will address your questions at various places in today's webinar, and the way to ask questions is via an online discussion board at tinyurl.com/using-containers. Please open this now if you haven't already and start the conversation. This document is open for comments and questions, and feel free to address other people's questions if you know the answer. This is a collaborative document, but we have a couple of containers experts there to help. Audrey Stott and Alexis Espinosa from Pawsey have generously offered to assist on the discussion board today. Questions put to the speaker will come from this document, so please don't use Zoom's Q&A or chat function. This document, the discussion board, will stay live after the event finishes for your future reference. And we'll also let you know when recordings of today's sessions are available on the YouTube channels of Pawsey and Australian BioCommons. Joining us today from Pawsey Supercomputing Centre in Perth is Dr. Marco de la Pierre. Marco's main area of expertise is quantum mechanical calculations and classical molecular dynamics. He has a PhD in materials science with a specialisation in theoretical and computational chemistry. He's a highly experienced software developer and has accumulated an extensive skill set around workflow automation, portability and reproducibility, including the design and deployment of container solutions for high-performance computing. Marco joined Pawsey in 2018 and his role as supercomputing specialist sees him engaging with researchers in the fields of computational material science, computational chemistry, and bioinformatics. He's a skilled trader, so we're very pleased he's here today to start off the series of webinars on using containers in bioinformatics. Welcome, Marco.
Thanks, Christina, for the nice introduction, and welcome everyone. It's my pleasure to welcome you today to this first seminar in a series of 3 on containers on HPC and cloud with a special tailoring for this bioinformatics audience. So Christina has already introduced you to what Pawsey Supercomputing Centre is and to his national profile as a Tier 1 HPC centre in Australia. Before I start this webinar, I'd like to thank you, some of my colleagues here at Pawsey, in particular Alexis, Anne, Audrey and Sarah, and also Brian, who was at Pawsey until last year. They all brought relevant and important contributions to this tutorial and materials. So let's get started with this first webinar, which is about some core topics on containers for HPC and cloud. This is what the menu looks like for today. So we'll have a short introduction on what are containers, why are we using them, how we're using them. Then I will start and guide you to some hands-on demo sessions along the basics of the Singularity container engine, which is the core tool we are suggesting here at Pawsey to use containers. Then there will be a session on how to share files between container and the machine, which is actually in practice this is what allows you to use containers for any real productive work. And then we get a short introduction on how to build your own customized container images, which will then be covered in more detail in one of the next webinars. So to get started, what are containers? So you can think of containers as a kind of units of softwares that encapsulate an isolated environment for a single application or a bunch of applications to run independently from what the host machine looks like. You can also think about that as, say, a full directory tree with directories and files, so a file system similar to what you have in all of your computers, except that this directory tree is completely isolated and able to be used independently. And so that's how you guarantee that your application will run regardless the setup of the machine you're using. So where can you run these isolated autonomous pieces of software? Well, almost everywhere, any hardware, almost any operating system. And so any site really, and any user can use the same container with really no big change in the way they operate it. The container technology was started a few years back in the IT and enterprise world, but in the recent years has become increasingly popular in the HPC world as well, so scientific computing. You might have heard of virtual machines. So just to add some points to the description of what containers are, we can make some parallel between containers and virtual machines. So VMs are a software tool that is able to virtualize the entire hardware of a machine. It means that it provides a piece of software that is able to abstract what the real hardware of a computer is and interface then to any type of computer you might use on top of. This means that this virtual machine needs to ship with the entire operating system, including the kernel, which is the core unit that makes any operating system work. But this also implies that virtual machines, because of their nature, are quite heavyweight to run. So they take a lot of resources in terms of RAM, compute power, and disk space. And it also takes some time to start them up and shut them down. On the other end, containers don't really care about, they're not able to, say, to handle different hardwares. They don't care about that. They don't deal with that. They only virtualize the operating system. It means they're able to interface with different operating systems without caring about the hardware. So what it means is that they basically share the same kernel, the same core of the operating system of the host, and they just build on top of that. And this might just suggest you this key aspect that containers are much more lightweight than VMs. It means they take much less resources to be run, so less compute power, less RAM, less space. And also they can be started and stopped very quickly. So this makes them a bit more ideal for high performance workloads where you don't want to waste precious compute time and resources just in starting and stopping the infrastructure that you use to run your applications. So the key tool that you need in order to run containers is then a container engine, which is exactly this piece of software that is able to make your container live. So to bring this isolated file system, put it on top of the kernel of the core of the host operating system and make it work regardless the machine you're working on. There are a few options available out there. So Docker was the very first solution that was developed, and it's really quite common and widespread in the IT world. It's good on PC, workstation, even on cloud. A newer solution is called Podman with similar features. But then when you go into the HPC world, you need some additional care, additional features to be included in the design of these container engines. And so here we have slightly different options. So here I'm just mentioning a few: Singularity, which will be the core of this webinar, Charlie Cloud, Shifter, and others. So these container engines are quite good to be run on HPC sites, but also on cloud and eventually workstation. So they're still quite flexible in terms of where you can run them. So why using containers in scientific computing and HPC, so including bioinformatics? Well, this technology allows us to enforce some good practices in running scientific workflows. And in particular, today, I'm just spending some words on reproducibility, portability, scalability, and I will also be touching on some aspects of productivity in a couple of slides. So first, reproducibility. So the matter here is we often, researchers need to run their analysis multiple times. You need to repeat them, and hopefully you wouldn't need the results that you obtain from the same inputs to be the same over time. So say you repeat the same analysis in the same machine, maybe with a different software setup, because meanwhile upgrades have been done, right? Or you want to run your analysis or need to run your analysis on different machines or sites. So here we're talking about portability, or you need your analysis to be run by other people, maybe your collaborators or some peer reviewers of your publications that need to double check your results. So here we're talking collaboration and shareability of your analysis. Containers are very effective at enforcing this, because by nature, as we said, they provide the entire software environment to run application as embedded in a single piece of software that you can run and you can ship and run everywhere on any machine. And this also has some quite specific advantages. Say, if you have software stack with a lot of dependencies, I'm saying just for instance, R Python workflows, but also other ones, it might become quite difficult to be able to version track all of the software you need to run your application. And in containers, you can achieve that quite easily because you're shipping everything all together at the same time, and you're not changing the software stack once you have first installed it. You're just basically redeploying the same piece of software in different sites. Then we have some scalability aspects. So you might have happened to you that you start and work on your laptop or on an office workstation, and you only have small samples. Then the amount of data grow, and you need to move your analysis to some other place. Might be an HPC, might be cloud. Well, the good news is these containers, these isolated pieces of software, can be shipped around on different machines, but also they can be scaled up to run at the same time on a large number of nodes, which means if your analysis really grow up in scale, you can very easily and natively run these pieces of software at scale without any change in the installation, which means we're saving quite a lot of time. And this is ensured, again, by design of the container runtimes that have been designed for HPC, such as Singularity. And then we have some productivity aspects. So I've heard stories of researchers spending literally weeks of their PhD, if not months, just to install software time. With container, you tackle this very well, because basically you solve the problem of installing your software once and for all. And then all what you need to do is basically to just ship or download the installation on a different machine, and you're good to go. And very often you'll find that the software you need has been already containerized by other people, so you don't even need to bother in installing it. It's basically ready to go for you. And this also includes all the software where just installing the dependencies, the prerequisites, takes a lot of time. Again, you solve that once and for all, and then you don't waste any more time just in installing packages. So how do you normally use containers? The starting point often is some web registry, so some public repository, which you can find on the internet, that collects containers that were built by other people. And these are just a couple of examples, Docker Hub and KidoTayo. If you look for your software there and you find it, well, all you need to do is literally to download it on your system and you're ready to go. And this happens, honestly, quite often in bioinformatics. We'll get back to this aspect later. The alternative, if you don't find the software you're looking for already in container form, well, you can spend some time in installing it in a container, so in building a container image. And then again, once the image is ready to be used, you will deploy it on your production system and use it for your analysis. Who is using containers at Pawsey? Well, right now we have a growing community of users of this technology. I'd say the biggest one is possibly bioinformatics, but we also have machine learning specialists, Python users, computational fluid dynamics engineers using OpenFOAM. And we also have people deploying RStudio and Jupyter sessions using containers. The software tools we're using are Singularity in our HPC, so you will find it pre-installed on all Pawsey systems. And as regards the Nimbus Cloud, so Pawsey Cloud system, we also provide Singularity pre-installed in all virtual machines, but we also install Docker, and we'll get back to the reason for this later on. So just some definitions before we get started with the hands-on session, because I'm going to use these words quite often. So we call image the actual shipping unit of containers. So think about the image as the collection of files that make your application work. This is the unit that we are shipping around, so we are building it before we use it. We are looking for it in a web registry. We are downloading it on the production system. This is the image. Whereas to be picky and precise, the container is a slightly different entity. The container is the actual instantiation of an image. So it's the process that you can spawn out of an image. So think about the container as the running application, as the open application that is carrying out the actual work. And then we have the registry, which is a place to store and share container images. There are a lot of public registries available out there, such as Docker Hub and KidoTayo, but you could also eventually build private registries if you need to ship software that can be shared with everyone. And finally, we have the Docker file of definition file, which is basically a specification for when you need to build a container image. It's basically the recipe that you use to build a container. And so just before I stop for a couple of minutes for some questions, let me just show you graphically how these web registries for container images look like. So this is the library from the Singularity authors. It's called Scilab Singularity Library. Here is the field where you can actually look for container. And so Singularity Cloud is not really interesting. It's quite recent, and right now the uptake is quite low, so it's not that interesting besides being shipped by the same authors of Singularity. Docker Hub is much more interesting. Here you can find a lot of starting images for when you need to build containers. So it can be operating systems such as Ubuntu, be Python, and basically use these search fields to look for containers. And then there is a third one that it's particularly worth mentioning with a bioinformatics audience, which is KidoTayo. And the reason for that is that you might have heard of BioCommons, which is a project to provide a package manager for bioinformatics packages. Well, BioCommons has also recently started a project called BioContainers, which is a porting of all BioCommons packages into containers. And KidoTayo is the place for look for biocontainers. So say if you're looking for BLAST, high chances are you will find it in KidoTayo as built and made available by the BioContainers project. And it is, say, item number 2 in the search list. So basically, I think there are literally several thousands of bioinformatics tools available in KidoTayo. So that's your first destination for every time you want to use containerized bioinformatics applications. So that being said, I'm just stopping for a couple of minutes in case there are any questions on this first part of this webinar today.
Okay, thank you, Marco. And we do have a couple of questions. I'll pose 3 if we have time. Why Singularity in that Docker? And there's a bit of conversation going on about security.
Yeah.
So.
All right. So, well, I will mention quite soon, basically in the next slide, why we are picking Singularity and not Docker. So, and maybe I will also mention a bit on security when I get there.
Okay,
so
great.
Hold on just a couple of minutes.
Okay.
And thanks for the question.
Another question. Can Singularity be used on a PC/workstation?
Yes. So actually, at the end of this presentation, I will share with you a link to the GitHub project that is behind the tutorial today. And there I provided instructions for installation of Singularity basically on a Linux system, on a Ubuntu OS, so that can be considered as a template for installation on Linux. So basically installing Singularity on any Linux system is quite straightforward. You need root privileges, so you need to run the installation with sudo commands, which means you can't install Singularity yourself on a shared system such as HPC. Administrators need to do that. But if you have sudo access to a machine, you can install Singularity quite seamlessly. For Windows and Mac users, the best way to install Singularity right now is by using a tool called Background. You need, again, root privileges. But again, I provided the installation instructions on the GitHub page of this tutorial. So stay tuned for that.
Okay. What will be more lightweight in terms of disk space and loading time? A Conda environment or a Singularity container?
I say possibly for a lot of applications might be similar. My take is that with containers, basically containers are a more general tool compared to Conda, because with Conda you're basically restricted to be able to install software that is already available on Conda, whereas with containers you can basically ship whatever you want, including Conda packages if you wish to, but you're not restricted to that. And personally, what I like more about a container shipping compared to a Conda environment is that it's more easily reproducible. Well, you can, with Conda, you can as well save and freeze your installation stack at any given time and just reinstall the same one again. But you need to be willing to document that yourself. Whereas with containers, by design, you get 100% reproducibility on the software stack. So you will be always ensured that if you run the same container image, you will be running exactly the same piece of software file by file. And with that, I think I will move on now to the second session, and I will also get back to that first question we had. So why Singularity on HPC? So Docker was the first container engine, and it is great. It's great for IT. It has got quite interesting features that make it even more powerful for some aspects compared to Singularity. But Docker has also some shortcomings that make it basically unusable on HPC. The major one is possibly the requirement to run Docker with sudo. So every Docker command that a user would issue on the shell would need sudo privileges, even for downloading an image or running an image. And this aspect alone makes it unusable on HPC, because administrators just can't let users of a shared facility to have sudo rights. So that's one of the main reasons. Singularity needs to be installed by administrators with sudo privileges, and parts of its runtime also need some sort of root privileges. But the key difference is that users do not need sudo privileges themselves to be able to run it. So that's kind of a security reason, if we want. As there was the question, let me just briefly mention that there is still a possible component of security issue, in that, as I said, some functions in Singularity are basically run by root. So what we are doing there is basically we're relying on the fact that programmers and developers of Singularity are doing the right things when they write the source code, and they are not leaving bugs in the code that might allow privilege escalation. So I'd say there is a potential concern there. What I can say is that up right now, there hasn't been any report of critical security breaches due to using Singularity and being able to escalate to root. It's definitely something to keep an eye on. Right now, it's not been a big real concern in practice. There are other good reasons for using Singularity on HPC. So Docker comes from IT, so IT folks wanted a tool that comes with isolation by default, and that's great to enforce a number of practices in IT, but in HPC and scientific computing, we are in a different context. We want the users possibly to have the more seamless user experience that they can have. And Singularity comes handy in this regard because it comes with integration with host by default, which means that by default, when you run a Singularity container, we are running with the same user name and user privileges than the host user. You are running in the same directory and you're seeing the same files as the directory you're running it from. You are, by default, sharing the same shell variables than the host, and you're also sharing the same network and communication port. This aspect basically translates in the user in the fact that the syntax that the users need to learn for using Singularity is much simpler compared to Docker, and that's because developers of Singularity did the work in making this default as more as friendly as possible, considering a scientific computing audience. And then also Singularity comes with a native compatibility with a number of interesting tools, such as job schedulers like SDEM and PBS for HPC sites, MPI for parallel applications, GPUs for GPU-enabled applications. So if you need to run or interface to this type of technologies, the amount of work you need to do as a user with Singularity is really limited, if not zero. The only drawback in using Singularity, or the main one, is about building images. Because of the way Singularity is designed, to build an image yourself, you will still need root privileges. So you need to run the build with sudo, which means right now you can't really build the Singularity image right from an HPC center. And so the workflow we suggest is actually to build images either on your laptop or workstation or on a cloud service, and then ship your image to HPC for runtime and production. And this is possibly, again, on the user side, the main drawback right now. I've already mentioned some useful container registries that you might be using to download pre-made images for your work. So I won't spend much here. And so let's now move to the first bit of a hands-on demo for today. We're going to cover the very basic commands of Singularity when using containers. So commands to execute shell commands inside a container, commands to enter into an interactive terminal shell inside a container, and then commands to download and store container images. So I now switch screen and move to a shell in my terminal. So today I'm gonna connect to a virtual machine on the Pawsey cloud, on the Nimbus cloud, where I prepared the material for this tutorial. So let me just do some housekeeping. This variable might be handy later on. You don't need to care about that. So I start and just change directory to a place where I'm running this first toy commands. So first thing we are gonna use for this very first example, kind of a silly container image. It's a Ubuntu image, so nothing really fancy. It's not a powerful scientific application. It's just a basic image that ships with a basic operating system. And I'm doing that because it's small to download, so it will be kind of a fast process, which will allow you to just see the basic commands of Singularity in action. So what I'm doing here, I'm using the Singularity main command, Singularity followed by exec, which is the Singularity syntax to execute commands. This is a Ubuntu image I'm grabbing from the library. And when library here is the Singularity Library, the first one I showed you earlier on my web browser. And then as a command, let me just visualize with cat the content of a file that is present on any Linux box, which basically just tells you the version of the operating system you're using. So when you run this command, you see if the image is not available on your computer already, it will download it from the library image. See here. And once that's done, you will get the output from the command. And here is the output of this cat etc os release. And you can see that I'm running Ubuntu 16.04, which matches actually the version of the container I was using. And this is also nice because I can run the exact same command on the host machine I'm using today, on the Pawsey Nimbus machine. And here you see it's a different, it's still Ubuntu, but it's a different version. It's 18.04. And this is just to give you a kind of first idea that I'm actually running two different operating systems. We have 18.04 on the host machine, but when I run instead inside a container, I'm getting something different. And because I'm actually running in an isolated environment, the container environment. So let's try some other execution commands. So you can basically really run any Linux command you would run on a Linux box, and it would just execute inside the container. An interesting thing to mention is that the Singularity Library, as I told you before, is not very popular. There are really just a few images in there. So the one that we will be using more often will be Docker Hub. And so you can download and use container images from Docker Hub with Singularity by prepending the Docker prefix. And you will see here again, there will be a process of downloading the image. This is quite important and interesting. So one thing to know is that Docker and Singularity use different agreed formats to pack and embed an isolated environment into containers, which means that, for instance, Docker is not able to run Singularity images because of this difference. On the other hand, Singularity is able to run both Singularity and Docker images, which is great. It means that it doesn't matter how you pack and ship your images, Singularity will always be able to run them. So it's quite compatible as regards the runtime. So that's why you got much more output in the process of downloading the container. That's because Singularity had to convert the Docker image from Docker Hub into its own format. And so here is a lot of output. The very last bit is creating CIF file. And here CIF just means Singularity image format. So what Singularity has done here was just to convert the Docker image into a usable form for Singularity. And then after that comes the command that I asked to execute. Of course, now it took a lot of time because Singularity had to download and convert the image. If I repeat the command again, it will be much faster. And that's because Singularity is able to cache the images that you use in the local disk. And so when you reuse them, the execution time will be much faster. All right, let's mention something more about this image syntax and naming conventions. So the first thing that we have here is the online registry we're using, so Docker in this case. Then we have a container image name, and then we have this string after the colon, which is called tag, which is normally used to specify the version of the software inside the container. One is actually also able to not specify the image at all, in which case the container runtime, Singularity in this case, will default to the last version, to the latest version of container that it can find on the online registry for that application, Ubuntu in this case. And we can get a proof of that if we use again our command to print the version of the container. And you'll see now something different compared to previous examples. You see it's still Ubuntu, as you might infer from the name of the image, but now the version is 20.04. It didn't take much time to run because I had used this machine before and the image was already pre-cached before this tutorial today. But the key aspect is that if you don't specify the tag, you just get whatever latest version is available on the registry. And there is an important point here. So you might think, well, that's handy, it can save you some typing, and you also grab always the latest and greatest version of any package. Well, in the end, we end up discouraging this type of practice when using containers. Because what happens is that you might lose in the reproducibility of your workflow, because basically the latest image in a container registry is something that can change over time. It's not under your control. It's the people that maintain the registry that might decide one day that, say, Ubuntu 22 comes out, and then the latest image becomes Ubuntu 22, and you don't realize that. And the software stack of your analysis changes, and your reproducibility is kind of compromised. So this is a possibility, but it's good to stay away from that, basically. So it's always good to specify the version, whichever it is, for the container you want to use. Then there is a couple of more comments I want to show you before moving on. So Singularity has a command, which is Singularity shell, that allows you not to execute an application or command inside the container, but instead just to open up an interactive shell inside the container. So basically, when you run Singularity shell, you are able to create the container and move with the shell inside it for whichever use. This can be useful, for instance, when you have just downloaded an image, if you need to inspect its content, if you need to get to know which type of programs and executables you can execute there. And we're going to use this command later also to inspect the actual content of the file system of the container. Once you're done, you can just exit the shell as you would do with a normal Linux shell, and this would close the container, stop the process, and move you back to the host machine. So one last comment to show you is Singularity pull. So as I said before, when you execute commands, Singularity will cache the container image somewhere in your local disk. But maybe in some software setups, you might instead prefer to organize the containers yourself inside the directories, maybe creating a directory tree which is organized by type of applications. So Singularity pull allows you to make a copy of the container image in a directory of your choice, which by default is just the current directory. And in fact, you can see here that after the Singularity pull command, this file has appeared, Ubuntu_1804.zip, which is just a copy of the container image we downloaded before. And so, for instance, now rather than keeping on using the full name specification for the container image, I can just run the container by using this file that I have downloaded. And that can be just a useful alternative to be aware of. Just one last word on the syntax, on the naming convention for a container on online registries. We used in these examples Ubuntu 1804. So basically, let's stick, for instance, with the Docker syntax. Here, Ubuntu was the name, 1804 was the tag or version tag, and we were with the Docker prefix. We could omit that because Ubuntu is a part of the general library in Docker Hub, but very often you would have one extra string in the container name specification, which basically represents the repository or say the name of the developers that developed the container. So it might be, I don't know, Rocker for R and R Studio images. We'll see that tomorrow. It might even be the name of a lab that has uploaded containers on Docker. Might be Pawsey. There is a Pawsey SC repository in Docker. If you use KidoTayo biocontainers, you will need also to add KidoTayo in the name specification of the container. You don't have to worry too much about that because when you look for container images on the website, on the web browser, on your registry, you will get prompted about the full syntax to use it. This is just for you to be aware of these different syntaxes. And that's it. I think now I'm happy to take a couple of questions from the audience.
Okay, so there's a lot of discussion going on. Great discussion. Just going back to container versus image, if you could just make that distinction again.
Yeah.
That would be good.
Yeah, so think at first this is kind of a bit confusing. In the end, we end up using the two words in an interchangeable way. It doesn't really mean much when you actually use them. It is mostly like for appropriate understanding and abstraction of the concepts. So think about a normal application you would download or install on your computer. You would have a directory somewhere in your computer which contains all of the files for your application. But then when you actually open the application, you would have a running process that runs on your computer that allows you, say in the case of Word, to open up a text editor and use it. So you have this distinction with normal applications between the files that you need to run the application and the actual process, the instantiation of the application. And so images and containers match these two concepts. So images are the collection of files that you need to carry over to your machine to actually use the containerized application. And the container is the running instantiation of that image. So it's the actual running process that you spawn, that you start up to use the application. And that's about it. In the end, it doesn't really matter if you mix the two terms. It's just that they are two distinct concepts.
Okay, thanks. One more. Marco, you mentioned scalability. I imagine Singularity containers need to be spun up for every task that I wish to run in a parallel. What is the compute overhead like for spinning up the container for every single parallel task?
Quite small, actually. So Singularity was optimized for that because it was designed for HPC. So we're going to see an example on the third webinar this week on Wednesday. The overhead is really minimal. So Singularity is able to interface natively with no extra care, basically, with the resource manager on your HPC side. And basically will behave as any other application. So you will have a resource manager that spawns not one, but multiple instantiations of a Singularity container. And that's it, basically. The overhead is really limited. One thing that personally took me just some time to realize is that even if a container can be, say, 1 gigabyte in size, because it has a lot of files, when you actually run it, you don't have to load all of those files in your memory, because it's really like just an embedded and isolated file system. You only pick and load the files that you need to run the functions and commands you need for your particular user case. So it's you don't have any overhead because of the fact the container is big, and same, you don't get any overhead because you're spawning multiple instances. It basically, as I said, behaves as any other application, which is spawned through a resource manager.
Okay, thanks. That'll contribute to that. There's a discussion, an ongoing discussion with that, so that'll be a good contribution to that.
All right, thanks, Sam. So keep on going now. So we're entering the third topics today. So far, as I mentioned, we saw just some very basic commands that allowed me to show you how to execute commands in containers, how to download them, how to open up shell. Now we still need some little pieces to be able to use containers to actually run any meaningful scientific analysis. And now we're going to cover a couple of important topics: how to share files between the host machine and containers. And there are special flags and the special environment variables for that we're going to see quite soon. And also how to eventually tweak and tune the sharing of variables between host and containers. So let's move back to the terminal and just ask ourselves some questions. So first question, so we'll use again for the time being the Docker Ubuntu image, just because it's small and simple. We're not getting distracted by any extra functionalities or applications. So let's ask ourselves, what does the file system, so the collection of files in the container, look like? So let's have a look at the content of the root directory in the container. And we have this collection of files and directories. Now let's have a look, so we can compare with the content of the root directory in the host machine. And what you can see basically is that they're different. So in the container, for instance, you have this singularity item that is nowhere to be found here, and vice versa. In my host machine, there is a snap item, VM Linux item, and so on. So this is just to show you in practice that the file systems in the container in the host machine are two different things. And that's what allows you to ship your application in an encapsulated, independent, autonomous way through containers. Another question, so where are we in terms of current working directory in the container? And we can use the pwd command of Linux to get to know that. Okay, and where are we in the host machine? Same place. So this is an aspect of integration I mentioned before. So by default, a container will run and execute in the same directory that you were previously in the host. Can we see the content of this directory? Yes, we can. All right, so by default, again, the content of the current directory is available in the container, which means, for instance, I can create a file. Touch is just a simple way in Linux to create empty files. So if I create a file inside the working directory, I get to see it in my host as well, because the current directory by default is shared between host and container. This is quite good, but let's see. So sometimes in a lot of file system setups, you might have some pieces of software or data information that is not sitting right in your current directory, but it's sitting somewhere else. And then thinking, for instance, about genomics databases, which are often installed in a system-wide available directory on shared file systems. And so that would not fall inside the current directory. So can we see directories that are outside the current directory from a container? And say, can we see this directory inside the container? Sorry, this was just a type of me. I left touch there. So the right command is just ls to see if we can have a look at the contents of the directory. Says no such file of directory. So maybe the directory does not exist. Is it maybe it was just me typing random stuff? No, the directory actually exists. So it has about 15 files in there, but we can't see them from the container. And that's because by default, the container will only share the current directory. So this can be an issue, right? We can't access by default these type of locations. Can we overcome that? So we can. So there is a flag in Singularity exec or Singularity shell that allows you to specifically and explicitly mount additional directories in your container. And so if I go like this, so after Singularity exec, I add -B and another directory. Well, I'm now able to see the content of that directory. And if I wanted to write files there, I could. So that's the way to make additional directories available inside a container. And it looks quite straightforward, isn't it? There is a small variation to this syntax in that you can even give the directory a different name if you wish to, and you can do that by adding a colon after the -B directory specification. And this basically means that you are now referring to that directory in the container with a different name. And I'm going to show you later a good user case for this syntax. Right, so getting the same result. And one last way to achieve this is by using an environment variable, which is called Singularity bind path. And basically you can feed the very same information there. And now you don't need the -B flag anymore. So basically it's a typing saver. If you know you need a directory basically often in your workflow, you can just define this variable at the beginning, and then you can save typing time later on. All right. One last thing on, so we now know how to make any directory we wish available in the container. A couple of extra comments. Never bind mount the root directory. So never do something like this. It would basically break the container, because then you would mount the entire host file system in the container, and then you would see an overlap of system files, system applications, and things would just not work anymore. So that's not a good idea. By default, at least in properly configured HPC centers, the home directory of the user would not be mounted in the container, and that's for kind of security reasons, especially if you are using the container to run web services, web sessions that might be accessed by third-party people. So the home often contains sensitive files, sensitive data, might be your SSH keys, other secrets that need to remain secrets in terms of the configuration of your access to that machine. So our suggestion is to always avoid mounting home. Do not do that. If you really need, there are cases where an application in a container needs some files in the home because that's the way it was designed. Well, you can always mount just a specific file from your home. Say you need a file in the home, you can just mount that one. So that way you are not mounting any sensitive data, you are just really mounting that single file or single directory that you need. Another way to achieve that, say there is an image that really needs a home, needs to write on that home, create new files and directories. Well, you can use, to that end, that syntax I introduced you before, where you are renaming directories between hosts and containers. So you can create a false home and name that false home as the real home in the container. So that's basically a trick, so that you make the home available in the container for the application that needs it, but that home is not your real host home. So there is no sensitive data there. It's just a service directory that you're using for the purpose of the application you're running in the container. So we could spend a lot of time and examples on this. Here I'm just giving you the basics of how to use this syntax to mount directories. Good. A couple of extra concepts that can be useful here. So let me go back to when I was just using directories in the container without mounting anything from the host. So here's just a quick question. Can I create files inside the container? So say in the container's root directory. No, gives me an error. It says cannot touch hello from root. And the reason is it's a read-only file system. So this is quite important, every container that is run by Singularity is a read-only system. So every directory and file that belongs to the container can't be modified. You can't create file, you can't edit file. The only files you can edit are the ones that reside in host directories, which is why it's so important to know ways of mounting and sharing directories from the host. That's the only way you can actually get a containerized application to actually produce some output, to do some work and save it for you to use later, all right? Okay. I think we have seen enough about sharing directories. I will just briefly mention, without examples, that, as we said, by default, you share the same environment variables between host and containers, which is good in a lot of situations, but there might be applications or cases where you want to that not to happen. So you want an isolated environment in terms of shell variables. And you can achieve that with a special flag, which is -C, that will basically cut out ties between the variables in the host and variables in the containers. And then if you still need to pass specific variables in these highly isolated containers, there is basically a singularity syntax for that, which is defining variables in the host with this prefix, singularity env _. I'm not going for an example today, but this syntax, I will reuse this syntax tomorrow in the second webinar in a nice example we're going to cover. So hold on to that, we'll get back. So now after we've seen how to run containers, how to share files with containers, maybe it's time to go for a practical example to give you the feeling that you can do some science for real with containers. So we're going to go for a science demo using BLAST, which I think needs no introduction to this audience. It's just a very, very popular tool in genomics analysis. So let me just move to the appropriate directory. It is ready for the purpose. So in this BLAST directory, we have a FASTA file, an input file ready for the analysis. And then in a separate directory, we have also a small database for BLAST that we'll need to use. But what do we need to achieve? Well, this is a very small example. So I've saved the protocol in this file just for ease of use today. We need to do a very simple thing, actually. We'll need to prepare the database for usage with BLAST with this command make BLAST db that maybe some of you have even used in the research career. And then after the database is ready, we'll need to run BLASTp to perform a search of sequence alignment between the FASTA file in this directory and the database file in the other directory. And we get that printed out in a nice output file. So we don't have BLAST installed in our system, as you see. So we want to use containers to this end. And so this would be a nice occasion to go on your web browser, open up KidoTayo and look for a BLAST container. Just to save some time today, I've done it for you this morning during coffee time. And I've just saved the name of the latest version of BLAST from inside the KidoTayo database of container images. So I'm going to use this guy to run this BLAST analysis today. So first thing, maybe we can just start and use the syntax we saw before. So singularity pool, just to make a local copy of the container image. It will run quite fast because I have pre-cached the image yesterday just to save some time today. So you can now see that we have a nice BLAST. So a nice BLAST image file here. We will need just some preparation in the BLAST database directory because the database is still compressed. So let's decompress it so we can use it. Yeah, and now I think we're pretty ready to run the demo. So with this database, and we saw, let me just review the analysis we want to run. We saw, well, yeah, the first command is to make the database. So it takes as an input this zebrafish protein database. We want to make the database compatible with the type prot. I'm being a bit inaccurate here. I'm not a bioinformatician by training, so apologies. So let's give it a go. So we want to run this command in the container. So let's just use singularity exec. And we have just downloaded the container for BLAST in that other directory here, right? It was called, here we go, BLAST _290 and some string. And then let us just paste the very same command we would run for any BLAST installation just as the command that we want to run in the container. And here we go. Yeah, it worked. So we just built the database using the containerized version of BLAST. You can see there are some extra files that appeared in the directory here. So the database is ready for usage. We can now go back to the BLAST directory where the sample input is. And so the next command we want to execute is the BLAST P command. I will just copy paste here to save me some typing. So let's do the same. We want to run this BLAST P alignment, and let's do it using the container that we just downloaded. So it will be Singularity exec blast 290 blah blah .sif, and then the command was BLAST P the query sequence, and then the database location. Here I'm just using relative paths, so it's under BLAST DB, the protein database, and our results. Do you think it will work? Database error. So what happens? It can't find the database. You might be surprised. You might not be surprised. Well, that's because I'm looking for a database that doesn't sit in the current directory. So here I need to use the host directory mounting syntax we just saw, say, no more than 10 minutes ago. So let me go back to this syntax, and after the exec instruction of Singularity, let me add a bind mounting flag to bind mount the BLAST DB directory. And let's see how it goes. Right? So that is just a warning, but now we didn't get the error anymore. So did we get our output? Yes. That's it. So we just ran a very small sample BLAST analysis by using BLAST. There was no BLAST installed on my host machine. All I had to do was to download a BLAST container from KidoTayo and use it. It's a time saver, isn't it? Yeah, open for a couple of questions.
All right, thanks, Marco. Again, a lot of good discussion going on in the Google Doc. One question, can I mount the external BLAST database to the Singularity, and how would I do that?
Yeah, so provided that the external database is available in the machine where you're running Singularity from, yes, you can. And it's basically the syntax you kind of just saw. So in our case, the BLAST database was in this directory. And so I used -b in the directory path to make it available. So now say you have a directory in your file system called data BLAST database, just as an example. Well, just add -b data BLAST database to your execution line, and that's it. Or if you want to just do it once and for all at the beginning of your analysis, you can just use the variable way of doing it. So export Singularity bind path and the path. One interesting thing here, so in the Pawsey file systems, we try and make the life even a bit easier for users. So Pawsey users might know that we have two key directories on Pawsey file systems, which are group and scratch. When you load the Singularity module on Pawsey systems, those two directories are bind mounted by default, exactly with this syntax, which means that everything that you might need that is found under those two directories is already available. You don't even need to care about mounting those directories because we have bind mounted them for you.
Okay. There is another question. It's kind of a clarification. So can you pass environment files with multiple env_vars to a container with Singularity. For example, with Docker Compose, I can load a .env file and the container will use its contents to set its environment variables.
Ah, yes, right. Unfortunately, so in the current Singularity version, unfortunately, you can't pass a single file with all of the definitions. And when I say current version, I think this is still the latest one, 3.5.3. But so Singularity 3.6 is been in beta version for like 2 months. And I noticed that one of the new features will be exactly that one. So you will be able to specify the variable, the mounting you need and variables you need in a single file and just provide that file. What you would do right now is Singularity, and I didn't mention that before. You can provide multiple mounting points by making a list which is comma separated. So this would work. If you need to mount 4 directories, say, you just make a comma separated list. And this would work the same with the -b syntax. So something like that.
Okay.
But I agree with you. I mean, being able to provide this list in a file and then just provide the file would be much nicer in terms of the user experience, and they're getting there.
Okay, thanks. Do you have time for one more?
Yeah, last question, maybe.
Okay, this is kind of taking it up a level rather into the coding. Reliability of pre-built containers.
Yeah.
How can you tell
Yes,
what they're
cool.
trustworthy?
Yeah, good question. So, good question. I mean, we have kind of discussed security before. What I can add here is will the container work or not? I mean, will the application was the application built properly in a third-party image or not? So, well, that's why, to an audience of bioinformaticians, I recommend using the BioContainers project. I consider it kind of a trusted source. Because basically the authors behind are the same authors of Bioconda. They've been curating the list of Bioconda packages, thousands of packages for years now, and now they're just converted and made available the same tool set in containers. So to me, they're the most trusted source of biocontainers images. So every time I look for bioinformatics packages, if there is the biocontainers version, here I am back on my web browser in the KidoTayo website. Yeah. If there is a biocontainers version, I will pick that one because I don't know the guys in person, but I know that the organization behind this project is quite cool and they do things quite well. You might still get some broken images, which means you run the command, it gives you an error. It happens to me with SAMtools, for instance. SAMtools itself works, but some other tools that ship with SAMtools don't. So in those cases, I just build my own image. So I ensure that everything is working as it should. A good practice that you might enforce is that when you download the image, you can run some very quick check. Say, can I run blast P from a blast container and get the output? Yeah, that's a good sign. I mean, if you can get the application to run a simple command, okay, there are good chances it will work. It might be more formal and even have a small set of input files that you can use for testing the containerized application. My take is that this procedure, even if you add this formal testing step with a small data set, it will still save you heaps of time compared to building the tool yourself. So it's well worth. And my experience, again, out of, I don't know, 10, 20 bioinformatics packages I'm looking for in biocontainers, maybe one is broken, the other ones will just work. So it's, to say, overall, the biocontainers project on KidoTayo is quite robust and it ships working containers.
Okay.
All right.
Thank you, Marco.
Thank you, Anne. Thank you, everyone, for the interesting questions. And now moving to the last bit for today's webinar. So I'm just going to introduce the topic of building a container image. This will become then the core topic of part of the webinar tomorrow, but today I'm just laying the foundations for that. So we're here in the case where, you look for your application on a web registry and you couldn't find it, or you found it and it was not working, or say maybe you need a container which is a bit more structured, maybe it's you're running a Python or R workflow, you need to tailor the packages that are present in the container, well, then you need to build a container image yourself. What I'm going to do now, I will execute this command, which is Singularity build, to build an image from a definition file, from a recipe. And then as it builds, it will take about 5 minutes. I will discuss some of the aspects that you need to be aware of. So let's move to the laughing directory. So we here have lolcow.dev. I'm going to use it today without opening it as a black box. Tomorrow we're going to inspect the content of that file. For now, all you need to know is that it's a recipe file. So it's a list of commands that you need to, that Singularity needs to execute in order to build the image. Let's do it this way right now. So we need to provide Singularity build with a name for the container. Let's call it lolcow.sif. As SIF is the standard extension for Singularity images, could be anything, it's just for clarity. And then after that, the name of the definition file. So I could have tried to run this without sudo and see what happens. I just was just willing to save some time. Let it go. Meanwhile, let us comment on what we're doing. So why did I need to issue sudo before Singularity build? So that's because by design, so due to the way the developers of Singularity coded these features inside the source code of Singularity, there is no privilege escalation in the Singularity usage, which means if you run Singularity, inside the container, you will be the same user than you were in the host machine. But point is, very often when you need to install software in a Linux file system, you need sudo privileges to run installation commands. But then this implies that, so if you need to run these commands that are in the definition file, if you need to run these commands with sudo, the only way to get it done with Singularity is to run Singularity with sudo. So in this way, you will be running Singularity as root in the container. There's no third way. So if you run Singularity plain, you will be the same user. If you run sudo Singularity, you will be root user, the same as you would be in the host every time you run sudo. And there's no third way by design of the tool itself. So that's why I use sudo before Singularity build, and we are going to see the content of the definition file tomorrow, and we can even comment further on that. But that's also why right now it's not possible to build images inside an HPC system, because every time you need a sudo command in your installation process, bam, you are out of the HPC system, because you would need to run sudo Singularity build, but you can't. All right. So this also builds back to the security discussion we had before. As I said, so this can kind of reassure people in terms of security, in that the only way for a user to escalate and get root privileges is whether you run Singularity with sudo. So which means if you're on HPC and you can't do that because administrators didn't give you the rights, in principle, you're not able to run any privilege command in the container. So that is kind of a reassurance. I will still leave the benefit of the doubt, just because this relies on a proper design of the source code of Singularity by the developers. So if there is a bug in the code and this is not enforced anymore, then you can get trouble, right? So this is important to keep in mind, especially for administrators of the shared facilities, not really for the users. Just quickly mentioning, there is indeed an option to build containers from an HPC center without sudo. which is by using the remote build option, where you basically add the flag -r. And what happens here is that Singularity sends your definition file to a Scilab's Singularity server through the internet. The image will be built there and then will be downloaded back to your machine. So this way, all of the sudo privilege commands are executed there because that environment is hosted and managed by the Singularity folks. And you don't need sudo locally. I haven't played with that much. It's an option. To me, honestly, the workflow of having a separate machine, such as a laptop or a cloud instance to build is not too bad, but other people might want to play with this one. So nice things about the Singularity image format is that, as you saw, a CIF image is just a single file. It's a big file, so a Ubuntu image might be 50 megabytes. The blast image, I think it was about 200 megabytes. You can get images as big as a few gigabytes, but it's still a single image. So if you need to share the image, say across different machines you're using, between cloud and HPC, between Pawsey and NCI, whatever, you can basically just transfer the image with any transfer and file syncing utility, you know, SCP, rsync, FileZilla, and so on. You could even, if you are like an organization with some infrastructure available, you might even just set up a dedicated server where you can host Singularity images as files. There's also an option that is provided by the Singularity developers, which is the Scilab's Cloud Library. There you need an account, which is free, but if you have it, you have the option to upload the images you have built up there so that they are publicly available by anyone that is browsing the library. And you do that with the Singularity push command. We are not demoing this just in the interest of time, but yeah, that can be quite useful. And it's a concept in its own. So here we are talking Singularity. If you were using, for instance, Docker to build images, the same concepts would hold, right? So once you build the image, you need to share it, and you have different ways of sharing it as single files or by uploading on a server. Cool. As we were speaking, the build finished. So you can see that we got to the end. It says, the last line say, creating C file, build complete. So just as the last thing before we close up and take the last round of questions today, let us use this image. We're gonna see tomorrow what was in the definition file, in the recipe. Today, let us just give it a quick go. So there's the installation. I did some utilities in the Ubuntu base image. Say we can run this fortune command that just produces citations. But then I saved this one because it was a bit hard to remember, but this is kind of nice. I like it quite a lot, and I think it's a nice way to close up today. So let's execute this one in the lolcout of CIF container. Right, so basically it's a way to get a colorful cow that likes citing James Joyce. Right, that's it for today. So back to you, guys, if you have any questions.
We do have a few final questions. So can I merge two existing biocontainer images to make one image? For example, if I wanted both BLAST and SAM tools in the same container?
So no, you can't do that. But that's fine. So what we recommend as best practice when you are using this type of standalone applications, BLAST, SAM tools, whatever, Trinity, whatever, we suggest the principle of one container per application. So you need one more application in your workflow, you just download the corresponding container. So you will end up in your machine with a collection of containers, and you will just use one or the other one depending on the application you need. And this is quite good for flexibility because it provides you with a modular setup. So say you have a structured workflow that uses different applications, and say you use Trinity for assembly. and then one day you realize you need spades instead, well, you just need to substitute one container with another one. All of the other containers that provide the applications for the other steps in the workflow remain the same. So as a modular solution, we suggest to go with one container per application. And that's actually how applications on KidoTayo are offered. So it kind of complies with this suggested practice.
All right, another one. Can Singularity run in the background? And if the process is interrupted, does Singularity resume where it broke?
So you can think of Singularity basically, so an application that runs through Singularity kind of behaves the same way it would behave without Singularity. So yeah, it's it basically. So if your application does not have checkpointing features, if the process is interrupted, you will need to resume it from start. If the application has checkpointing features, that's better. So if it gets interrupted, it will, you can then resume it from the last checkpoint. But that's basically that's transparent to Singularity. You will get the same behavior that you will get for that application without the container. As regards running in the background, yeah, I mean, if you need to, you can. And again, it's the same as any Linux process. So you would use the same syntax you use for normal Linux commands to go in background.
Okay. One more Pawsey specific. Is there a web page with containers used on Pawsey? For example, machine learning containers or other containers?
So right now, so in the Pawsey user documentation, there are a couple of pages that just basically present the basic commands I showed you today so that people can get started with containers. We have right now our policy. So we do have some images that we curate ourselves, but we are trying to keep this at a minimum. So we have, we'll see them on Wednesday on the third webinar. We have a couple of images that we build and curate ourselves, but otherwise you can basically run any container image that is available on public registries. So right now we are not restricting that in any form. So you can basically browse the container registries online and pick the images, and you can make your own on your laptop and then ship it to Pawsey and run it. The same good usage practices hold as for any application. So if you break the usage policy, you will be responsible for that. But currently we don't have any restriction on using containers. We will discuss very briefly a couple of suggestions on useful container images between tomorrow and Wednesday.
Okay, and then one final question to wrap up, I guess, kind of a nice way to wrap up, and there's been a lot of discussion around this in the chat. Containers, are there situations, instances where they're really well placed to be used and situations where they might not be the best choice?
Yeah, I'd say it's a balance of benefits and disadvantages. So we see two main advantages. So one is time saving in terms of installation times. That can be a very good reason to move to containers. And the other one is, as I mentioned in the first slides, about enforcing reproducible and portable workflows. And I believe this one is very important in bioinformatics because these days a lot of analysis in this domain, I think they require, they would benefit a lot from reproducibility and portability. So using tools that naturally enforce these principles, I think it's really an advantage. You can combine containers with other tools that enforce reproducibility in the protocol of research you're using. And here I'm thinking about workflow tools such as Nextflow or SnakeMake or others of this type. If you combine containers for the software and workflow tools for the protocol, you can really design and eventually publish and make available fully reproducible and portable pipelines, which I think are really a plus in research these days. And so that's to sum up, this is why we are strongly recommending bioinformaticians, researchers in health, life sciences, agriculture to use containers. We're talking here about data-intensive workflows with structured pipelines. You guys use a lot of tools in these pipelines, and you will need your analysis to be reproducible. So great usage case. The same might hold for data science, let's say. We are suggesting it to machine learning guys because of installation times, mostly because I once tried to install TensorFlow on our systems and I don't want to do it again, honestly. And similar things for Python and R workflows. So again, saving time. With Python and R, it's mostly about being able to manage dependencies and conflicts between versions of packages, but also reproducibility of the pipeline when your workflow needs, say, 100 to 100 libraries to work. So just this last slide, as I promised. So these slides are built out of a larger tutorial that I have designed over the past few months, which sits here in this link. I can send it off to Christina so she can share it with you. So here is a tutorial. It's basically self-paced, so you can run through it on yourself. Some of the episodes, in particular 1 to 4, cover the same topics of today. And other topics from tomorrow and Wednesday are also covered there. But for each topic, you will also find additional examples and exercises. And there is a corresponding GitHub repo, which you can clone, and basically it gives you all of the input files you need to run the examples in the tutorial. So we'll send this to Christina for sharing. And yeah, thank you all for attending today. It's been a pleasure to be here and to take your questions. Okay. Interesting discussions. Thank you.
Thank you, Marco, for the presentation. Also, thank you to Audrey and Alexis for answering the questions. To Christina and the Australian BioCommons for partnering with us to do this presentation. If you have additional questions, we have a weekly Ask Me Anything Pawsey hour. It's a virtual open door every Monday from 10 to 11 o'clock in the morning, Australian Western Standard Time. You can register for that on pawsey.org.au/events. We have specialists there, such as Marco, who are available and ready to answer questions. You can sign up to be a Pawsey friend to hear about other things that are coming down the pipeline. And feel free, if you've never been to Pawsey, to take a virtual tour at tour.pawsey.org.au. Thanks again.
Well, thank you. And thanks to the audience for joining us for the session today. We hope you found it useful. We particularly are appreciative of those who joined us on the discussion board. We'll spend the next 10 minutes or so in there tidying up the questions and answers in the document, so that can be available for your future reference. It'll stay live. We'll also let you know when the recordings of these sessions will be online, and we hope you'll join us for tomorrow's session. So we'd love to see you back here for part 2, customizing your containers. You can register for that now on the BioCommons events webpage. Just before we finish off today, we'd like to acknowledge that the Australian BioCommons and Pawsey Supercomputing Centre are enabled by NCRIS. And we'd also like to give our thanks to the Government of Western Australia and BioPlatforms Australia. Thanks once again, and goodbye.